Okay, we're going to talk about reaction quotients, which are very similar to equilibrium constants. This little activity is a good way to kind of introduce it. I recommend trying to do this on your own without me talking through it. And it kind of introduces you to the idea of the reaction quotient. So I would go ahead if I were you and pause and go through this, and then I'll kind of talk about the answers. We've got the system. It's an equilibrium system, obviously a reversible reaction. The K value is about 1,000. So that means that, yes, there's some of everything present, but there are going to be more products than reactants. So, all right, I got a 5-liter container at 25 degrees Celsius. I got 0.05 moles of PCl3, 0.02 moles of Cl2, and 0.2 moles of PCl5. Now, notice I did not say we are currently at equilibrium. I just put in that much of all of them. A needle is inserted into the container, and I add an additional 0.06 moles of PCl3 into the reaction mixture. What's gonna happen? Well, if you get a system at equilibrium and then you do something to it, you add some in or something like that, what's gonna have to happen is it's gonna have to get back to equilibrium. And if you remember from that simulation that I used, things are gonna bounce back and forth until it reaches the correct ratio. And this is a constant. K is a constant at a specific temperature, in this case, 25 degrees Celsius. The ratio has to be 1,000. So how are we going to figure out what happens? So at the instant of injection, before any chemical reaction takes place, what is the total number of moles of PCl3 in the container? All right. So let's see what we got going on here. Okay, I guess this kind of isn't worded the best because it says this one, and this one are at equilibrium. Okay. So I'm going to kind of draw this out just for my own frame of reference. So that means I've got, say, this 5-liter container, I'm making it a circle, and it has currently at equilibrium 0.0500 moles of PCl3, 0.0200 moles of, oh, sorry, that's Cl2, and 0.200 moles of PCl5. It should be, if I were to plug these in to my K equation, I would get 1,000. And if you do that, you would. Again, molarity is not moles, but I digress. Okay, so a needle is inserted into the container, and an additional 0.0600 moles of PCl3 are injected. So if this was at equilibrium, now when I add some more, what's going to happen? And I'm going to walk you through that. So at the instant of injection, before it goes back to equilibrium, how many moles of PCl3 are in the container? Well, I added 0.06 to the already 0.05. So now I have 0.110 moles of PCl3. That means the new concentration of PCl3 is 0.110 moles over the container is still 5 liters. So I'm at 0.022 molar PCl3. So that's what happens when I injected it. Now, I have not reached equilibrium. I added some stuff in, so it's got to re-equilibrate. So is the system still at equilibrium? No. Okay. You could say, how do you know? Because I added extra of one species, whatever species it is, that's going to throw off my K value, and K is a constant, so that can't happen. You could also calculate it. You're going to get that your K value is not 1 times 10 to the third. Okay, if you plug in this as my molarity for PCl3 and the other two, you're not going to get 1,000. That means I am not in equilibrium. Okay, what you would have calculated there is called the reaction quotient. So if I want to predict which of the following will happen to the moles of PCl5 after I injected the extra PCl3. So like, what happens if I inject extra? So I injected PCl3, which is a reactant. So to get back to equilibrium, what's going to happen? Well, some of this is going to have to turn into some of this so that my K value can re-equilibrate. Okay, so what's really going to happen is number 2. PCl3 and Cl2 will now be consumed to form more PCl5 to reach equilibrium. Explaining your reasoning. All right, so I could either say in words, I would say you added in reactant, right? I added in stuff that is more on the left side. So it's going to have to react and make some on the right to even back out. So it will react or get used up to create product and re-equilibrate. Right? I got to get back to that value. Now, mathematically, oh, missed a D. Mathematically, I'm going to show you how it works out, and we can explain it mathematically. You don't have to do it both ways. I'm just kind of trying to give you a different perspective. K is always products over reactants, right? At equilibrium. So if I were to add in some more reactants, right? I added in physically more reactants. Well, some of them are going to have to turn into products so that this gets back to whatever the constant is, because again, it is a constant. So if I added that in, it will make more products to balance back out to the same K value, because it is a constant. It needs to get back to that. So some of these are going to have to react to form some of these to get back to the constant. All right. Now, this whole thing, what we're talking about here is stressing an equilibrium system, doing something to it, and it's going to re-equilibrate. This is called Le Chatelier's principle. We're going to do a whole video on Le Chatelier's principle. So what I set up here, we were calculating these. This thing is called the reaction quotient. That's what this whole activity is about. So we're going to use the reaction quotient. So if I were to start with both reactants and products, I want to know what's going to happen if it's at equilibrium or if it's going to do something to reach equilibrium. We can calculate what's called the reaction quotient, and we're going to call it Q. All right. Now, the reaction quotient, or Q, is calculated just like K, but it doesn't have to be at equilibrium. It can be calculated at any time. So the reaction quotient is maybe not at equilibrium. I added some more of something in, I can calculate the reaction quotient still. Okay, so Q is calculated just like K, calculated like K, all right? Products of reactants, exponents, all that jazz. But it doesn't have to be at equilibrium, but does not have to be, I'm just going to put EQ. Okay, so it can be initial concentrations or something in the middle, that's fine. So if you're not sure something is at equilibrium, you can calculate the reaction quotient. And then what does that tell you? Well, if you calculate the reaction quotient and your Q value is greater than K, that would mean, so let's think about what it is, right? Q slash K, the way that we calculate these is essentially products over reactants. So mathematically, if it is too big, if Q is greater than K, that means I have too much stuff on top. That would mean I have too many products. The value is too large. So if Q is greater than K, that means there are too many products, right? Our number on top is too big. Okay, so what's going to happen? Well, it's going to have some of the products turn into reactants to balance back out to the right value. And if products are turning into reactants, that means things are going backward. So the reaction is going to have to go in the reverse reaction to reach equilibrium again. Okay, so this means, oops, reaction goes left or backward to get to equilibrium, okay, to get back to the K value. Now, of course, the opposite would be true if Q is less than K. That means it's too small. That means I have too much on the reactant side. I have too much down here. The value is too little. So it's going to need to shift to the top in order to be a larger value. So this means there's too many reactants. That's the bottom, right? Mathematically, you can see how that kind of works out. So that means the reaction goes forward to get to equilibrium. So if you're not sure which way the reaction is going to go, usually we're talking about reactions going forward, but they can absolutely go backward. They're reversible. So we can calculate Q and determine which way it's going to go. So we're going to do that here in example number 11. For the following reaction, K is 25 at 900 Kelvin. Again, We don't need the temperature for calculations. It's just at a constant temperature. So determine which direction. So you can say left or right or toward products or toward reactants. I don't care which way you say it, or you can literally put an arrow. The reaction will proceed or shift forward or reverse to get to equilibrium. So if I'm not at equilibrium, I can calculate Q, not K. So if I have moles of everything, right? I have this, this, and this. I didn't say it's at equilibrium. So instead of calculating my K value, I will be calculating Q. So I'm going to plug these values in. I've got 0.1 moles, 0.05 moles, and 0.2 moles. However, they do have to be in molarities. And I was nice enough to give you 1 liter. So the molarities are the same as the moles. So I'm going to do products over reactants. This is my product. So SO3 squared. So SO3 is 0.2 molar. That one is squared over reactants. SO2 squared. So 0.1 squared. And 102, so 0.050. All right, so you go ahead and calculate that, and you're going to get that the Q value for this particular set of concentrations is 80. Now, how does 80 compare to 25? Well, it is much greater than 25. So Q is greater than K. That means it's too big. So I have too much stuff on top. It's going to have to shift to the bottom in order to balance out, or products are going to have to shift to reactants. Or you say it's going to have to shift left. Any of those things are true. So if Q is greater than K, it will shift reverse or left. Okay, this is the answer. Okay, or you can say will shift, however you want to say it, it's totally fine. It's going to have to go the other way in order to get to equilibrium. Okay. Now, for some people, this is hard to like visualize or mathematically figure out which way it's going to shift. You can also just memorize it if you wanted to. If Q is greater than K, it shifts left. If Q is less than K, it shifts right. That's always going to be the case. Some people remember it because of the way that the mouth on the greater than or less than is opening. If it's opening to the left, it's going to shift left. If it's opening to the right, it's going to shift right. That is the case as long as you do Q is greater than or less than K. If you flip them, of course, it doesn't work. So you're totally welcome to memorize, but it is nice to understand why it's going to shift that way or that way. So B and C, I recommend calculating yourself. You do have to calculate the molarity before you plug them in and then figure out which way they're going to shift. So I would go ahead and do that now. And then I'm going to show you how they would get set up. So your work should look something like this. I'm just literally going to plug in the moles over the liters for these. Oh, that's 3. You do have to calculate the molarity. If you do not include that 3 for the volume, you're going to get the wrong answer. So you cannot just plug in moles. You can try it if you want to. I promise you're going to get a different number. So be really careful with your parentheses. Plug out on that end. This one's going to be 1.13, which is, of course, less than 25. So Q is less than K, means it will shift right, okay, or forward. All right, and the final set are only other like option of things that we will see. And so I did this on purpose so you could see what happens. If you calculate Q down here, so 0.25 over 5 squared over 0.25 over 5 squared, 0.245. You get that Q is 25. Well, if Q is 25, that means that we are at K. That means we're already at equilibrium, so we're not going to see any shift. I'm already at equilibrium. I have the right set of proportions. I'm not going to shift forward or